everyone! In this video, I'm going to walk you through the process of how to graph your data for the surface area to volume of three types of cells. For this graph, you are going to need the surface area to volume of the sphere, the cube, and the column from the previous pages, so make sure you have those ready. So for this graph, we are going to calculate the surface area to volume ratio of the different sizes of cells. So we're going to make a line graph. In fact, we're going to have three lines on this graph, one for the sphere, one for the cube, and one for the column. So I've marked off a random area on this graph where I'm going to indicate the surface area to volume ratio based on the size of the three types of cells. In other words, the surface area to volume ratio is our dependent variable, and the size of the cell is our independent variable. Once you have your scales for your y and your x-axis, we're going to start with the surface area volume ratio of the sphere. So when you did your calculations, you calculated that at 1 micrometer, or the size of 1, the surface area to volume ratio of the sphere was 3. Then at a size of 2, the surface area to volume ratio was 1.5. At cell size 3, the surface area to volume ratio was 1. I'm going to go ahead and put the dots in for the rest of the size of the cell of the sphere. So when you connect the dots, this will be the shape of the line. Now I'm going to do the same thing, only using now the data of the cube. Starting with the cube that is 1 by 1 by 1, the surface area to volume ratio is 6. Next, for a cube that's 2 by 2 by 2, the surface area to volume ratio is 3. Now I'm going to fill out the rest of this graph and connect the line just like I did with the sphere using the data from my calculations. So here is the line for the two sets of data compared so far. You'll notice that in both the case of the sphere and the cube, going from 1 to 2 has a very large drop off here. Look at the slope of the line right here. It cuts in half essentially. So we go from 3 to 1.5 and from 6 to 3. So now let's see what happens when we graph the data for the surface area to volume ratio of a column. The surface area to volume ratio of a column that's 1 by 1 by 1 is going to be the same as a cube that's 1 by 1 by 1 because it's equal size. But when we increase the height of the column by 1, in other words, the column is 1 by 1 by 2, the surface area to volume ratio is now 5. So as you can see, increasing the size by 1 did not cut our surface area to volume ratio in half. It did decrease, but it didn't decrease as much as it did from here to here with the sphere cut in half. From here to here cut in half with the cube. It did decrease, but not as much. So now I'm going to go ahead and put in the rest of the data for the column. So as you can see, the shape of the line for the column doesn't have that dramatic drop-off that we saw with the sphere and the cube. As I mentioned, when we go from size 1 to 2, the surface area to volume ratio essentially gets cut in half. That doesn't happen with the column, and you'll also notice that you don't see that steep, dramatic drop-off with the column. The surface area to volume ratio stays pretty high. So in conclusion, if a cell is going to be larger, but still maintain a very high surface area to volume ratio, then the type of shape of cell you're going to want is a column, because a column will maintain a high surface area to volume ratio even if the cell gets larger. Thanks so much for watching, folks. I hope this video was helpful. Bye.